So before I start, I wanted to tell you a little story. I was, my laptop, as you can see, has this big sticker on top that says SQL. It looks like one of those country stickers they have on your cars, and it says SQL. So I've been about 2 weeks ago. I went to SQL Bits in Liverpool, that wonderful European conference, SQL Server conference, and I was flying BMI to get there. And the cabin crew, very nice people, showing the typical British humor, so very funny. And the purser, the main steward, looks at my laptop, and he goes like, SQL, what airport is that? You know what? I actually checked. It's San Carlos, California. So, my name is Maciej Pilecki. I'm a SQL Server certified master. Any other masters in the room? Show of hands. Few. Okay, very good. Microsoft SQL Server MVP. Any other MVPs? Show of hands. Okay, there you go. Very good. So I do travel internationally for consulting, for work, for training, for conferences. I spent half of my life on the airplanes at the airport, so I totally understand what airport is that comment. And I kind of come back here to a conference like this, bringing back some experiences from real life world, trying to fix problems for my customers, all the different kinds of stuff that I encounter. So some of the demos that I will be doing today actually are not real customer scenarios, but they come from a real life scenarios that I've done for my customers and the lessons I've learned back there. If you want to contact me, here's my email address. Come later, ask me for my business card. You can also follow me on Twitter. The handle is Dr. House of SQL, which probably tells you a little bit about my working style. I'm ruthless, but I deliver. Okay. And I love going into a room full of developers and telling them why their code sucks. I can explain that very in great detail. All right. So what's the agenda for today? I want to talk generally about what the optimizer does and what happens there. Why we need execution plan caching and how we can control that. What we can do both in terms of settings on the database and on the server, so it's a kind of a DBA side of things, but also as application developers, what the database application developers can do to improve execution plan reuse and what impact it will have on performance. I will also tell you when execution plan reuse might not be a good thing and what you should be doing about it, if there are ways around that. I will briefly go over re-compilation and what to look for, and general optimization hints and stuff like that. So I hope you will find this very interesting. So let's start with the query execution. What actually happens when you hit F5? Query is sent to the server, the results come back, ultimately. Maybe, yes. It depends, actually. So what really happens in there is that every query that comes into the server goes through a number of steps. And I will take you, today I'll discuss everything that happens up to the point where we're ready to execute. So I'm interested in everything that precedes the actual execution of your query. So let's concentrate on those steps for a second. The first of all, we have parsing. So parsing involves breaking your batch into individual statements, checking the syntax, if it's actually in our language, if we understand that, if it's legal transact SQL syntax, doing name resolution on that as well. So trying to figure out if it makes sense. By the way, SQL Server parser up to this moment has been a little bit more complicated, and because of that also less maybe efficient sometimes, than some of the competitors. The reason for that is very simple. There is no need or there is no requirement right now to terminate every statement with a semicolon. Right? So up until SQL Server 2008 R2, you're fine putting like 1,000 statements in a single batch and not separating them with semicolons. So parser has to figure out where one statement ends and another begins. Unless, of course, you're using merge, or you're using a CTE, or you're doing send or receive using service broker. Right? There are 4 exceptions right now that do require a semicolon. But these are exceptions. Right? Otherwise, those keywords could be ambiguous. So just to make sure that we understand what you're doing, we require those. The SQL Server requires those semicolons. As of SQL Server 2012. Not using a semicolon is deprecated. Which means you don't have to do that in 2012 yet, but potentially in the next version, you will be required to use a semicolon at the end of each statement, which is a great thing. So start doing it right now, get into the habit, because it also makes the code a little bit more readable. Right? People from other products, the O thing, they use it a lot. So you should understand that. And get in the habit. It makes the code easier to read, but it will also make the parser simpler later, because you will know where your statement ends and where it begins and where it ends. But for now, we don't have to do that. So we can put a batch full of statements, and it will execute. The parser will have to figure out where all those statements, how many statements you have there, and what they're doing. So once we have parsed the transact SQL or the batch, figure out the individual statements, the next thing that happens is called algebraization. It's a difficult word, really. It's a component, algebraizer. I think that's the correct pronunciation. That basically takes your transact SQL statement, your query, and turns it into a tree that explains the logical meaning of your query. It's a kind of like figuring, what the poet had in mind. Someone wrote this query, what they had in mind, what were they trying to achieve. So it turns it into a query that explains what logically we're trying to do. That tree describing the logical meaning of your query is an input into the next step, the optimizer. The query optimizer takes that logical description of that algebraizer tree, the logical description of your query, and tries to figure out the best way to actually physically execute that. So now it's turning a logical representation of a query into actual physical execution plan. The algebraizer says what we're trying to do. The query optimizer decides how we're going to do it. And this is, of course, the most interesting step in many ways. So we'll be talking about it a bit later. So once we have an execution plan, the optimizer came up with an idea of how we want to execute our query. We're ready to execute, and we submit this plan for execution. This is, of course, a super simplified version of things. Each of those steps could be divided into smaller parts, and you could go into details. But it's kind of, for now, it's enough to know that much. Now, the query optimization, being the most interesting of those, is basically a process of selecting an execution plan from many possible candidate plans. So there's, for a complicated query, there might be thousands of ways how we could execute it. Are we going to, in which order we're going to join those tables, which indexes we will use, what join algorithms we will use to join those tables, etc., etc. So all those decisions are made by the optimizer. The optimizer tries to find the best plan. SQL Server has a cost-based optimizer, which means every plan that we consider has a cost attached to it. It's an estimated execution cost. What we think it will take, how much resources it will take, and how much time it will take to execute this query in this way. And then we try to compare this plan against that plan and say, oh, maybe executing it that way is a better way because it's cheaper, right? Takes less resources. So that's the general idea. Since SQL Server 7.0, the query optimizer does not actually guarantee the best possible plan. It tries to find what is called a good enough plan. A good enough plan is such that is relatively good and seems to be fine for executing our query. It comes from the fact that at some point you get into this kind of law of marginal returns, where you could invest a lot of resources and a lot of time to find a better plan, but that better plan would probably be only marginally better. So it's just the return on investment wouldn't be there. So at some point the query optimizer says, okay, I've spent enough time on this, I've got something, it's good enough, let's go with that. Let's not try to come up with another 1,000 possible plans to find one that is maybe a little bit better. So there's no guarantee of actually getting the best plan every time. Good enough plan is good enough. So we're trying to find this, that the one that has a smallest of the ones that we come up with, candidate plans, we're taking the one that has the smallest estimated execution cost. That's why we have a cost-based optimizer. But there's a problem with that. First of all, the optimization can go wrong in many ways, right? It's not an exact science. The most important thing you have to understand about the optimizer and the costing that the optimizer uses to choose a better plan over a good one is that it estimates the cost of execution. Probably guesstimate would be a better word sometimes. The query optimizer says actually no idea how it will really play out once you start executing this query, right? It tries to guess it based on your statistics. So you have the data distribution statistics, you know how big your tables are, roughly how many rows are there, how many pages they had allocated, and you have those distribution statistics. And if those distribution statistics are good and stuff that you're doing in your query can actually be accurately estimated, then it will take the value of your parameter or whatever you're trying to find in your table and say, okay, there will be 155 rows that fulfill this criteria. So we will have so many rows going in. It actually estimates the number of rows and the size of those rows flowing through each operator in your execution plan. And each of those operators has a cost based on that number of rows and the size of the data, etc., etc. But we have no way of knowing for sure. We're basing this estimation on statistics. Those statistics might be wrong, because they might be no statistics, right? Sometimes we're just lacking statistics. Those statistics may be stale, so they've been, last updated 2 years ago, or 6 months ago. That was the last time when we updated statistics, and we've been updating our data ever since. We've put a couple 100,000 rows in that table, and the statistics are still not refreshed. So there is a whole bunch of data in this table that is not even reflected in our statistics. One of the problems with the statistics is that right now the threshold for refreshing statistics for big tables is 20% of the table size. So if you have a table that has 1 million rows and you build statistics or refresh statistics on that table, let's say you rebuild your index. As part of that index rebuild, you will refresh the statistics. So you have this 1 million rows represented in your statistics. Your next refresh, automatic refresh of statistics, will happen after 200,000 updates or inserts. Which means I can put 200,000 new rows in that table and it's not going to be reflected in my statistics. What if your statistics are on something like your date column and then you query for the last week worth of data? But your statistics were updated a month ago. So the entire last month is not even there, right? The statistics say that your data ends 1 month ago. And then everything that is beyond that, no, there is nothing like that in the table according to statistics. So then the query optimizer says, okay, oh, you're looking for the data for last week? Okay, that's going to be 1 row. Holy crap, it's 200,000. What are we going to do about it? Well, nothing. Just happens. So there is no, it's not like query optimizer, says, okay, we have absolutely no idea, so we're going to just estimate 1, which is as good estimate as any other, I guess, if you don't know. And then, it's okay, we have this plan, and we decided that it's going to be 1 row, so we prepared this plan for 1 row. Then we start executing it, and the moment we start, touching the data, it turns out it's 200,000 rows. It's not like we're going to go back and come up with a new plan. No. We have to go. The moment you start executing, you have already committed yourself to executing that plan. It's not like you can, let's go back because we've learned something new about the data, and let's recompile with this new information. No. Because that would be in a vicious circle probably very soon. So whatever the optimizer comes up with, that goes into execution. And if your estimate is wrong, that means your entire costing for that plan and comparing plan A with plan B were based on false information. So maybe that plan that seemed to be a worst one, right, because it had a bigger estimated cost, is actually a better one. Because, well, if you have 1 estimated row, what the optimizer is going to do? It's going to go for instance, for nested loops. Well, joining 1 row to anything other is simple. You just take nested loops and you're done, right? 1 iteration, you're done. The problem with nested loops is that they're probably not going to scale for 200,000 rows. So you have those problems that they're very difficult to address, really. So you have to remember that optimizer isn't a perfect piece of software. It's trying to guess and trying to do its job based on a very limited and sometimes outdated information. We will have to help optimizer in many cases. So a wrong meaning suboptimal execution plan might be chosen by the optimizer because it seems best, right? The optimizer does it does best effort, right? It thinks this is the best plan, right? For 1 row, that would be the best plan. And that's what we think we're going to have. And then it turns out we have a lot more rows. And this is not a good plan anymore. Question here.
You have 2 servers with very different characteristics. Like one has a very fast CPU, big cache, big memory, but really slow disk. And the other one is memory constrained, slow CPU, but the guy just bought SSDs.
Yes. So the question is, well, if you have different hardware that has different characteristics, one server has a lot of CPU power but slow I/O. The other one has less CPU power, maybe less memory, but has a very fast SSD, etc., etc. Will the optimizer take that into account, right? Will it say, okay, so on this server we have to save on I/O, but on this one we can go crazy with I/O, right? But we want to save on memory. Nope. It's not going to take that into account. There are those costs for different operators and for different operations are hard-coded. Right? There might be changing from version to version as the hardware changes. I'm not exactly sure, but they are hard-coded in the optimizer. So optimizer basically has some weight it attaches to, doing I/O or logical reads or et cetera, et cetera. Question?
Yeah, well, you said it makes no sense, and I agree with you and the optimizer that once you find out that you got screwed data statistics, you should not go back. But could you mark that you went wrong here and kind of the next time?
Yes, I see. So the question is, okay, once we found out that we were so vastly wrong about the number of rows, we don't go back. But can we then, save this information somehow? It says, okay, next time, don't repeat the same mistake, right? Nope, it doesn't work this way. There's no feedback mechanism right now. But I've been talking to Microsoft people about this and suggesting that we could have a feedback mechanism like this, and we could have a way of finding all those plans where optimizer went badly wrong, and then what was the reason it went badly wrong, right? Because it's typically going to be lack of statistics, outdated statistics that do not reflect your data. It might be data skew. It might also be what you're doing in your query. There's certain stuff, there are certain operators, and there's certain syntax that is just not very good for optimization, right? It's just, you do stuff, and you use certain transact SQL constructs that cannot be estimated very well. And whatever you do there, the optimizer just doesn't know. One of such very popular examples are multi-statement tabled value functions. It's like a piece of code that returns some rows. It's like a storage proc that returns a table. But the query optimizer never looks inside. I mean, that function has its own execution plan. But when we have a query that consumes the results of that function, we have absolutely no idea what's going to come out. We're going to put some parameters in, and some rows will come out of this function. How many? Well, we don't know. So, 1. If the optimizer doesn't know, it goes 1. Why not? Right. Neil, you had a comment?
Yeah, statistics obviously are very key to getting an optimum plan. And obviously, we know at the moment 20% threshold, that's pretty stuck. There is the improvement coming forward with the trace flag and the 2012 finale that's going to do the proportional done on the size of the table. And it's going to be much easier to get stats that update themselves automatically based on that.
So Neil is making a comment that there is an improvement coming in 2012 in Denali, that the trace flag will, there are already existing trace flags that address some of the problems with statistics, especially if you have data that is monotonously growing, like that date thing, right? There is a trace flag that, I don't know the detail, it does something to help you with this kind of problem where you have a whole range of data that is not reflected in your statistics, the last couple days, et cetera, et cetera. But ultimately, you probably want to be a little bit more aggressive in refreshing your statistics. Statistics do have their limitations, but I don't want to talk about that right now. It's like when you do partition switching. Statistics are not per partition, right? So if you do partition switching, it's not like you're going to have these statistics that will switch together with your partition. So once you've done partition switch, in or out, doesn't matter, you should actually rebuild statistics on your entire table. Well, that's not what we have partition table for, right? To do a maintenance on this entire thing. So it's there are some certain issues or challenges there. So for the optimizer, that plan seems best based on this limited information. That information, unfortunately, is false, so we get a wrong suboptimal plan. How to look for those types of problems? We don't have we don't have a clear, there's like an event that would fire saying like, we underestimated the number of rows by a factor of 100,000. But you can sometimes check for that, and I'll get to that. Basically, you have to look at what was the estimated number of rows and what was the actual number of rows in your execution plan. So what do you do if the optimization goes wrong? Well, you have to outsmart the optimizer, and this is difficult, right? It's tricky. It's dangerous, right? It's a double-edged sword that can backfire, and well, it takes a lot of effort, right? Because you would basically have to take a look at, well, if you do query tuning and this query is going wrong, what's wrong with it? Well, it's going wrong because the optimizer underestimates the number of rows. So what are we going to do about it? Well, you have to be the optimizer then. You, with your understanding of the data and knowing what might be coming out of your table, you basically force the optimizer to give you a more scalable plan. So you would put like, for instance, you would put a join hint in there. You will say inner hash join, because you want to have a hash join there, knowing that there will be a lot of rows. Even though the optimizer thinks it's going to be one row and the nested loops will be perfectly good, no, you have to force it. Things like that happen. I'll tell you a little story later. So, what do we have query optimization for in general? Well, to create an efficient execution plan, or to find an efficient execution plan. In most cases, the optimizer will do a good job. We'll take your query and we'll figure out a way how to physically execute this query, what access methods to use, what indexes, what joins, etc., etc. And it's going to be a lot better than what you wrote, right? If we took your query and the engine would execute your query the way you wrote it, so for instance, using joins in that order, it will probably, in most cases, not be very good. Right? If you ever want to test it, there's a hint called force order. And then we'll join it in the same order as you specified in your query. So you can just take a look at that and you will know how bad it might be. So the query optimizer generally does a great job and comes up with an efficient way to execute our queries. Good thing. So optimization is a good thing. Improves performance, gives us better response time, faster queries, less resource usage, etc., etc. Yes? It's the same. So, okay, so the question here basically boils down to what's the difference between the estimated execution plan and the actual execution plan? And is it the same optimizer? Yes, it's the same optimizer. And actually, in terms of optimization, there is hardly any difference. So the estimated execution plan is where you ask the optimizer to come up with the execution plan, but not actually execute it. And then the actual execution plan is when you took that plan and you actually executed it, and you gathered all the runtime real statistics. So you get the actual number of rows, versus your estimated number of rows. There are situations, of course, where certain stuff cannot be estimated. Well, if you create objects in your batch, for instance, right, like you do create temporary table or maybe declare a table variable. Oh, actually, for table variable will work, but you do something in the query that means that your entire query cannot be actually optimized and compiled at once. It's called deferred compilation, where you actually have to start executing it, and once you created your temporary table, we can actually then compile the part that is referring to your temporary table. Because up until now, we actually didn't have that object. So now that we have the object, we can do a deferred compile, meaning we can compile the stuff that refers to whatever you created. So that's a subtle difference that sometimes you actually have to start executing before you get everything compiled. But in general, there is no difference. What the estimated execution plan gives you is what is going to get executed. Okay, so generally, optimization, good thing. But, okay, there's a couple buts. it's hugely expensive. Both in terms of CPU, it just takes a lot of cycles to come up and do all this complicated logic or do all those crazy transformations on your query and figure out how to use it. It takes a lot of memory as well, because you have to keep those plans, right? You have to load the metadata. You have to keep the plans that you're working on, etc. And it just takes time because of that, right? So coming up with a good execution plan takes a lot of resources on your server and takes a long time. How much time? Well, it is not uncommon to see a query that takes longer to optimize and compile than to execute. You will see it very often. A query that takes maybe 2 or 3 seconds to compile, and then it takes 500 milliseconds to execute. If you want to see an extreme case of that, I can show you. Actually, let me show you how expensive the compilation is. So I have this little application here. It's a little app that I point at my server, and let me show you what I execute there. It's I basically execute a query that looks like this. So either I execute this select query as an ad hoc query, putting a parameter value right in the query, so not parameterizing it, but just building up the query with the parameter value embedded in there. Or I can execute that through a stored proc. So this is the same thing in the stored proc. Now let me show you how it goes. So 10,000 queries, each with a different parameter value, executed against my SQL 2008 instance. It's a 10,000 queries, right? It takes a while to execute. No, that's 10,000. That's okay. But it is slow, as you can see. So what is happening there? Well, I have those 10,000 queries. Each of those queries, even though for us they look identical, they just differ by the parameter value, from the engine and from the optimizer perspective, each is a separate query. So each of them has to go through all those steps. Each of them has to be optimized and compiled. And there is a 80 kilobyte execution plan that gets created for each of them. And then it gets put in the execution plan cache. And then it's executed. And I think my server is just warming up because it's extremely slow. Yes, a question. Well, wait. Hold that question, okay? We'll get to that. We'll get to that. So, slow, right? This is a slow application. How slow? Well, we'll see in a second when it finishes. There's another question here.
You're in that query, they're selected back there, right?
Yeah.
You're in the query selected in the background there?
Yes.
So what do you use for the parameters?
This is just an integer, right? So this application goes in a loop and just basically goes with an integer from 1 to 10,000 and puts it as a value. None of those values actually returns any rows. I execute this query 10,000 times, I don't get a single row back because all of them get you 0 rows. But they still have to come up with those 10,000 execution plans. And it takes, what? Seriously? No, that wasn't 10 seconds. No, now I'm wondering. No, you know what? I am running on a battery. That might be the problem. That might be the problem. All right, let's try it again. I'm going to clear my cache. Oh, that's better. You see? I think it was a CPU use. Probably my CPU got throttled down because I was running on battery. A question back there. No. The query I've shown you is parameterized, but the query that is executed by the application is not. I said it clearly. I said it clearly. I'm putting the parameter value right in the query. I'll show you the queries in a second, right? So this gets 10,000 different texts. There's 10,000 different SQL texts being executed here, which leads to 10,000 optimizations and 10,000 compilations and 10,000 execution plans that go into your cache. Question?
If I profile this, when I see duration, does that include optimization time?
Yes. Like if you do a profiler, your duration will include the time spent by the in the optimizer. It's even better than that. The profiler is smart enough that if you have like statement completed, you get duration, you get reads, right? You get CPU. The reads actually include the reads that are used or taken during optimization. So when the optimizer reads the metadata, it's included in there. So you will run the same query twice, and the first execution will have a couple of reads more than the second one. How is it possible? Right? I'm doing exactly the same thing. So why is my first execution taking like 5 reads more? Well, because you have to read the metadata that is needed to come up with the plan. So this is 32 seconds to execute 10,000 queries. Now the same 10,000 queries through this little storage proc, right? So I'm executing exactly the same queries. I'm still getting 0 rows, but I'm executing it through a parameterized storage proc. Bang. Sorry? I didn't have to. I didn't have to. So now this difference between 30-something seconds and 1 second was for one reason only. That reason is called optimization and compilation. In one case, I had 10,000 optimizations, 10,000 compilations, 10,000 executions. In the other case, when I used the storage proc and I reused the execution plan for that storage proc, I had 1 compilation, 1 optimization, 10,000 executions. There is another problem here. When I did that, look what happened. The size of my execution plan cache went to 900 megabytes. Right? There is 10,000 ad hoc plans. Each of them is 80K. Actually 88, I believe. It's 88 kilobytes per plan. And it's a simple 2-table query. Right? It's nothing fancy. Just bang, bang, done. But it takes a lot of time. And then when you cache each of those plans, it takes a lot of memory to cache it. And we'll talk about that more. Whether the storage proc has only 1 execution plan, and let me show you that. And those of you that have been to Kalen's session, you've already seen those DMVs. I'll be talking about them more in a second. I basically use the DMExec cache plans, and I cross-apply SQL text to get the text of the query, and I apply DMExec query plan to get the XML execution plan. Actually, in this case, I don't really need the execution plan, so just to be quicker, let's do just the text. And what I get here is I get my storage proc right here, and that storage proc says use count 10,000. So it was executed 10,000 times. And this was executed 10,000 times, and it's 98 or 90-something, 96 kilobytes. Down here, there are individual plans, and I have 10,000 of them, and the only difference between them is this value back here, right? So everyone, this is the only difference, the parameter value. But I injected the parameter right into the text, so it's a different query every time. And each of those plans was executed once, but each of them takes 88 kilobytes. How do I know it's 88? because it's in the multiplies of 8K. It's in 8K buffers, so it's basically 11 buffers from your buffer pool. But if you want to see the extreme case of that, here's a little query that I've built in TempDB. I created 257 tables. And I have this query that goes, does a join on 257 tables. There's nothing fancy, right? Those tables have no indexes, right? They have hardly any data. There's like one row, maybe, or not even that. And so there's nothing really complicated about executing this query. But it's actually, in SQL Server 2005, that would be your limit. Trying to execute that in SQL Server 2005 would tell you, maximum of 256 tables per query. In 2008, you can go wild, and you can have more than 256 tables per query. So let's see what will happen. Actually, I've seen something similar. I had this client in Germany a while back, and I started looking at their execution plans. The query would look normal. Like, okay, couple tables. But those are not tables. They are views. And those views have like 8 tables inside, and some of them are not tables. They're actually table-valued functions. So by the time it all gets unpacked, you have this enormous execution plan. And I'm like, where the hell do I begin to tune that? Like, I have no idea what it even means, right? So this huge execution plan, and I'm like, okay, guys, I know there is a 256 table limit. I don't understand why you're trying to hit that limit. So, oh, come on. I didn't get everything here. No, I'm missing something here, obviously. All right, let me clear my cache and do it again. I think I know what I should do. I should say go here. There we go. That's better. So now we will see what happens, right? You see that there's one row returned there. So it's a simple query. Well, relatively simple as a 257 table query can be. And it takes almost 17 seconds to compile. And you know what? Why only 17 seconds? Because the query optimizer actually times out the moment it arrives with a first possible execution plan. And then it says, okay, I'm done. So it takes it 17 seconds just to come up with a single plan, and then it says, okay, I'm not going to look for another one. Just go with that. Metadata, something else going on my server. I mean, it's not like those execution times are deterministic. I might have been waiting for something. But you see, it took 17 seconds to compile and optimize. It took 83 milliseconds to execute. That's an example of query that takes quite a while. But you will see a lot of queries like that. In your production, in your applications, you will see a lot of queries that actually take longer to compile than they take to execute. So now the question is, do you consider compilation and optimization time in your performance tuning strategy? Do you ever think about it? That will make or break your application, oftentimes. We'll see what I can do with my application. By the way, you know what is... Okay, I'll get to that later. Well, just think about it, and if someone comes up with the idea what I can do for the optimizer in this case, I buy you a beer at GameWorks. So, it's expensive, takes time. I proved that. It's throttled at the server level. Because it takes so many resources to protect the overall response time and the overall stability and performance of the server, the optimization is throttled. You cannot just have any number of queries optimizing, because you would be spending all your CPU and all your memory on optimizing, and there would be nothing left to actually execute that stuff. And if you want to see this, there is a KB that describes DBCC memory status. And there is an optimization section that describes what you can find there. And what you can find there is basically this. If I execute it, it's best to execute it with results to text because it returns a lot of data. Yada, yada, yada. And one of the things it will show you, it shows you the optimization queue, and then it still shows you the small gateway, medium gateway, and a large gateway. Each of those gateways, depending on your hardware and the amount of available resources, will have a smaller number of units available. And those units are basically queries that can compile. Each of those gateways is effectively a choker. And as your query goes through an optimization and needs more resources to optimize, it has to go through that gateway. And that gateway, in my case, the first one will let 4 queries pass. The second and the third one, each will only let 1 query pass. Of course, on your server, on a bigger server, those numbers will be different. But there is a limit. You can only, in my case, I can only have 1 big query optimizing at the same time. So if I fired 2 of those huge queries, one of them would be waiting in a queue even before the optimizer looks at it. How do you know you have a problem there? There's actually a wait type called resource semaphore for query compile. If you're waiting on that, that means you're waiting in an optimizer queue. A question?
Is there any parallelization of query plans?
Parallelization of query plans or parallelization of the optimization?
Of the optimization.
Yes. So what you've seen is basically how it's parallelized, right? You can have multiple queries being optimized at the same time, but there is a limit. It's throttled, right? At some point it says not more than 1, or not more than 2, or not more than 4 at a time.
In a case like that, can you just force going order or pass from the first row to shortcut the compilation?
You can. Well, not fast first row, but you can do some stuff to optimize the optimization time. So I call it optimizing the optimizer. And I'm not sure if I'll have enough time here today to talk about it. But come later with questions. I'll show you some examples. So you have an influence over optimization time. I'll show you a little bit of that later. So if you see resource semaphore for query compile, you are likely doing too many compilations. Your stuff is waiting in a queue for the optimizer. There's a question over there in the back. Yes, there is a threshold that, so the question is there a threshold that says after so much time, just use whatever we have? Yes. There is an internal timeout in the optimizer. Right? So that's my next bullet, actually. Thank you. Your optimization can time out, which means the optimizer tries to do its job, and then it says, we've already spent too much time on that, and it gives up, effectively. Every execution plan, well, not every, because sometimes you don't, but most of the execution plans will have this attribute that is you can see it in the XML execution plan. You can see it in the properties of the plan. Let me just quickly show you. If I go back and execute my crazy query, right? So now I'm taking advantage of the fact that I have my plan. See, bang. Wow, that was fast. Why? Because this thing was cached, right? I just saved myself 17 seconds of compile time thanks to the plan caching. So that kind of introduces our next topic, of course. But one of the things, right, you have this beautiful execution plan, and we can say zoom to fit, and then it looks something like that. right? There's like 256 nested loops over there, you know, one stacked on top of the other. So it's like a beautiful stair. But if I click on the properties of this plan, well, not connection parameters, but come on. I want this. Rows returned, yada, yada, yada. No, I'm not getting it. Never mind. So let me show you that in the XML. So every execution plan can be, is described or can be described using this XML that basically shows you what it is. What you see in the Management Studio is just a graphical representation of this XML. The Management Studio actually grabs that XML from the server, and then it displays it using this beautiful graphical execution plan. So, you know, we have all those operators down here. It's like this thing is probably a couple megabytes, actually. We can actually check that. Let me see. That's going to be interesting. How big is this plan? This plan is 5.5 megs, a single execution plan. So this execution plan up here has this very interesting attribute that says statement optimization early abort reason. Why we basically bailed out and says, okay, we're done. And you can see a couple possibilities there, and they're all described in the books online. One of them is good enough plan found. And that's an acceptable answer. It's like, it found a good enough plan, or what it believes to be a good enough plan, and went with that. Another possibility is a timeout. So there is an internal, undocumented timeout threshold in the optimizer. So a period of time after which the optimizer will say, I'm done. I'm not going to spend any more time on this. And goes with whatever plan it found. Let me just quickly show you what Microsoft says about that.
Quick question.
Yes, quick question.
Earlier on in class, it was schedule 0, 1, 2, and they go to 0, go to 1, and then if it timed out in 1, he was stating that it would go back to the best plan in 0, and I asked the question, would it not just go back to the best plan out of 0 or 1 or before the timeout?
Don't know answer to this question. Really, I'm sorry, but it's too internal. So, basically, Microsoft says that there are possible values, timeout, good enough plan found, and memory limit exceeded. So yeah, there are 3 possibilities. So if it's memory limit exceeded, you obviously have a problem because you run out of memory trying to optimize this thing. Well, it's bad. Good enough plan found, good. Timeout, Microsoft says, no action is necessary. No. So basically what the timeout means is what I already described. And the official Microsoft statement is that no action is necessary. It's normal. Some of your plans will time out during optimization. But here's the problem. And I've seen it. Right? So I could probably even reproduce it and show it to you and prove it that you sometimes will get a suboptimal plan. Why? Because your plan actually hasn't gone through all the stages of optimization. It timed out because some of the more interesting tricks in the box were tried. So in my case, it was an index view. We had this perfect index view for the query. It would never get picked up. Why? Because the optimizer would time out before it even considered that stuff. So then what we had to do? Well, we had to be smarter than the optimizer. And we had to force that index view by basically putting it in the query using a hint and telling the optimizer what it has to do. Because it never arrived at some of the more interesting optimizations and timed out before that happened. So the question is here, who do you trust more, me or Microsoft? You cannot overwrite this timeout. I don't even know what the value for that timeout is. I've heard it is somehow proportional to whatever is the first estimation of the runtime for the query. So they figure out what their first estimation is. It's going to take so much time to execute that. And then when the time for optimization exceeds that by a factor of something, then they time out. But whatever it is, really, I have no idea. I'm not sure if they know. Query optimizer is so complicated, it borders on black magic. They are afraid of making changes in the optimizer to avoid the butterfly effect. Because improving something in the optimizer can have an effect on the stuff that is right now that you see in production, and maybe some of your plans will get better, but there is absolutely no way for them to know for sure if there will be no regression. They're going to put this nice improvement in the optimizer, and 10 of your plans will get better, but 1 will get disastrously worse. And then who are you going to blame? So there is this trace flag that is described in the knowledge base article. I don't remember the number. I'm not going to look for it, but it's easy to find. There's a trace flag that enables optimizer improvements. So they actually have bug fixes. They improve stuff in the optimizer. It's not on by default. Because the most important thing about the optimizer is getting stable and predictable results, right? You want the optimizer to come up with the same plan every time. And if you do some stuff in the part of the optimizer and it affects another part of the optimizer, you may end up with a completely different plan. And there is no guarantee that that different plan will actually be better. You will see stuff getting worse. So the good example of that would be SQL Server 2000 SP4, where they did certain stuff to the optimizer, and then all of a sudden a whole bunch of queries got a regression problem, and your indexes were not getting picked and stuff like that. So right now, they're very wary of doing anything with the optimizer because it can have those dramatic effects. So that's why I say, I think even people in the Microsoft don't really have the full picture of how it works. Yes? $41.99 is the flag. So trace flag 41.99. Thank you, sir. So, for all those reasons, we need plan caching. We need plan caching to avoid optimizing every query that comes in. Because we just don't have capacity to optimize every single query, especially when your queries take 17 seconds to optimize. So a plan caching is basically an attempt to save on those resources and on the time to optimize and on the optimization effort by reusing the execution plans. We come up with this plan, and we're going to use it for everything that executes this stored proc, or everything that executes a query that looks exactly like that, etc., etc. The execution plan generally exists of the, or the cache consists of the actual execution plan, that you have one execution plan for your query. It might be, it's read-only, right? Nothing changes there as long as it stays in cache. And then it might be used by multiple users. Each user will need its own execution context that describes basically, what we're doing here, what are the values for the parameters, etc., etc. Those execution contexts, temporary objects that you have, etc., etc. This execution context is cacheable as well, but it's one per user. So if you have like 10 users executing the same query at the same time, there will be one execution plan and 10 individual execution contexts for each of those users. Those execution contexts are cacheable and reusable, but they can be used by one person or one query at a time. The plan cache is sometimes called procedure cache, which is a little bit confusing because it's not only the procedures that get cached. So let's call it plan cache. I actually call it procedure cache a lot, but it's plan cache. It's execution plan cache. How do you know what's there? There's a whole bunch of very interesting DMVs that you're probably already familiar with. So sysdm exec cache plans is the main one. It basically shows you the content of your entire execution plan, execution cache. And then dm-exec SQL text gets you the text of the SQL text for your query based on the plan handle or SQL handle. dm-exec query plan gets you XML, the XML describing the actual execution plan. dm-exec plan attributes give you a table that describes all the attributes for your plan. I will show you that in a second because it's very important. And of course, we have dm-exec query stats that we use a lot in our performance tuning. dm-exec query stats has one row for every statement in your plan. So you will have multiple entries there, multiple rows for every execution plan. So we can, of course, aggregate this and combine them and do joins and aggregate them in some very interesting ways, especially on big environments. There was a lot of databases, a lot of queries, maybe multiple applications. You can find interesting stuff by aggregating and aggregating this and trying to, for instance, find how many execution plans do we have for a particular type of query, or how many plans do we have per database, etc., etc. It's an interesting experience to look at that. Since dm-exec cache plans, the most important columns there is, of course, use counts. How many times this thing was executed? That's the most important information that shows us whether that cache plan is actually usable. If we don't reuse that execution plan, it's dead weight. It only occupies memory. So we don't gain anything by keeping it around if we don't reuse it. So we want to look, the guys that have a high use count are the good guys, and the guys that only have one are the bad guys, because these are plans that were executed once, and then we put it in cache, and they stay there, and we never reuse them. Size in bytes, obvious. Type of cache object. And you will have a couple different types of objects there. The compiled plan, which is basically your execution plan. There is also a compiled plan stub that I will show you what it is. It's not really a plan. It's just information about the fact that a query like that has executed, and there is no plan for it. It's used with one of the options that I'll describe later. Parse tree is for views, defaults, check constraints, and stuff like that. Extended storage program, that's obvious, and CLR, that's obvious as well. These are, of course, not real execution plans. So we're only interested in the first two here. Then the object type is a bit more interesting, because you have ad hoc. That's your ad hoc query. Then you have a prepared statement, which is that's still an ad hoc, but it's an ad hoc that has been parameterized. Right? So it can be reused multiple times independently of what the parameter value is. But it's still effectively an ad hoc query, just a one that has been parameterized, either explicitly or by the server. We'll get to that in a second. And then the proc is basically anything that's an object. It's not only the storage proc, a function will also say proc, a trigger will say proc. It's basically a procedural execution plan. And of course, you have a plan handle that allows you to retrieve the plan from cache. Very good question. So what is the difference between a SQL handle and a plan handle? I'll get to that in a minute, but there is a separate cache for the actual query text. It's called SQL Manager cache. And this is where the text of your query is stored. And the text of a query to a plan is one-to-many. You can have exactly the same textual query generating multiple plans. Yes. You will understand why in a second. Actually, let me go back because I don't want you to read this slide just yet. And the plan handle is that particular execution plan. SQL handle is the text that generated the actual query text for that execution plan. And you store this text once, and for that text, for that query text, you can have multiple plans, right? So you can have one-to-many. Again, this is an interesting experience because you can get all this information from those DMVs. So you can run a query that will aggregate it for you and tell you that, oh, we have we have this particular query, or we have this particular query hash, and we have like 10,000 plans for this thing. Why would it be? And I'll show you an example. Yes? No, you can not have multiple queries using the same plan unless you have, well, in a way you can, but I'll show you that in a second. So, the query, yes?
If I execute a stored procedure that creates a parameterized dynamic SQL query.
Very good question. Very good question. So if you have a stored proc, and that stored proc builds up a dynamic SQL and then executes it through either execute or SP execute SQL, a parameterized query, that is an ad hoc SQL. So it would go, it has an independent execution plan. The stored proc has its own execution plan, and then that nested dynamic SQL that you execute through SP execute SQL has its own plan, right? It actually has its own execution context and its own execution plan. So that means the proc will have a proc plan type, and the dynamic thing inside will have a prepared object type.
Would that be reused?
That would be reused. So how do you check? Right, the query comes in, and we want to find out whether we have an execution plan for that query. How does it work? For an object, it's simple. It's an ID of the object. Whatever that object is, whether it's function, stored proc, or trigger, we basically look for database ID such and such, object ID such and such, and then we know whether we have a plan for that stored proc in cache. For anything that is ad hoc or prepared, as I already told you, there's small difference. Effectively, they're both ad hoc. So anything that is not an object comes in, and we hash the query text. We take the entire query text, we hash it, and that's our object ID. So that means that you need an exact textual match. Everything matters. White spaces, casing, anything, right? You add a white space in between, it's a different text. It's not going to match. New execution plan. Right? Whether you write orders with a small o or a capital O matters. These are two different queries. They, of course, resolve to the same object, right? If you're running a case-insensitive server, but technically the text of the query is different. So these are considered to be different queries. If you want to avoid this problem, you put your developers on case-sensitive server, which is really mean because it forces them to write everything in the right casing. Apart from this, apart from the exact textual match, there is a number of different attributes of the plan. They're called cache key attributes. They have to match. The most important are set options. Right? If you execute with quoted identifier on or off, matters. The same query generates a different execution plan depending on what set options were set on the connection. Database ID. Well, guess what? Executing select star from orders in two different databases probably means something completely different, because those two queries, they have exactly the same text, but actually resolve to different objects. So you will see exactly the same text, but a different plan, because it's so. If you execute in a context of a different database, it's obvious that you will resolve to different objects. Language and date settings. So whether you use US English or Italian or something like that will matter for your plan. The same for date settings, right? How do you interpret your literals, for instance? And, very interesting, user ID. I don't have time to actually demonstrate this, but if you don't qualify an object with the schema name, what you mean depends on who you are. If I execute select star from orders, it might resolve to a different object than if any of you would execute the same query. The same exact text, but depending on what is your default schema, it will resolve to a different object. So again, your query text is ambiguous. And what you are actually execute depends on who you are. And then you have a query that is specific for a user. So Alice executing select star from orders, one execution plan. Bob executing select star from orders, they might be resolving to the same thing. But we don't know, so just to be sure, we actually generate a separate execution plan for Bob, and then for Charlie, and for Deborah, and et cetera, right? So you go like that, and everyone has its own execution plan for exactly the same query.
Then why not use the schema name?
If you do use the schema name, then it becomes unambiguous, right? It's clear what you're doing. And in that case, you will see that the user ID in your plan attributes is -2. Right? It goes negative because it means it doesn't matter who you are. This execution plan is basically universal, can be used by any user. But you have to remember, everything in your query must be schema qualified. And there are actually a couple of other reasons why everything in your query should be schema qualified. So again, if you want to force it, have the name resolution for your developers to point to an empty schema, just something like default schema foo, and then they will have to type that DBO or something, or I don't know, orders or something, or otherwise it will not resolve. Let me show you that very quickly. So the basics of the plan caching means that if I run this in AdventureWorks, and I have those two queries, right? I have those two queries, and I get a single execution plan for both of those queries. Why? Because what kicks in is called simple parameterization. The query optimizer is smart enough to figure out that 43661 in my query actually meant, it's a value that is a parameter. It's a simple query. It's safe for parameterization. Basically, there's only one execution plan that is really possible there. It's a simple single table query. And because of that, I get a single execution plan that covers both cases. Nice. Safe plan, generally, yes. Yes, the safe plan, the plan that is safe for parameterization is a trivial plan. So in this case, of course, we can click and we can see that we're doing a clustered index seek, and then in the properties, it will tell you that the optimization level is trivial. Yes? Point zero second. Oh, sales order ID, yes. If I have like this would be a different plan. Why it's going to be a different plan? Well, because I'm using a different data type, of course. My data type does not match, so I have a numeric here. I have one plan for integer, another one for numeric. So you have to be careful here. But another interesting thing that happens here, if I now set quoted identifier off, and I execute the same, basically the same queries, what will happen is now I'll get another execution plan. I'm getting actually a bunch of them, but here's one, and here's another one. They do look the same, right? The text looks the same. So why do I have two of them? It's row 13 and row 5. So let me see. Let me grab the plan handle for both of them. Row 5, that's my plan handle. I'm going to put it here. Oops. And then row 13 is my another execution plan. And if I compare the attributes for those two plans through DM exec plan attributes, right? I grab the attributes for those two plans, I match the attributes, show them side by side, you will see that one of the cache key attributes does not match. And that is the set options, right? I turn on my quoted identifier on, bang, same query, different plan because my attributes do not match. all of those cache key attributes have to match exactly, or there is no match. And the plan does not get reused, and you get a new plan. So you may have a single query text and hundreds of different execution plans because some of those attributes don't match, right? Because it's different users, it's different database, it's different set options, etc., right? So you can see that user ID right here, -2, right? If my query was not qualifying the table name with a schema, there would be a positive user ID there, meaning this execution plan is for a particular user because the name resolution works for that user. Question here.
Yeah, how come it was able to figure out that it could parameterize that query, but not the one used in your simple little app?
I'll answer that in a second. We'll get to that. Yes, that's basically the same question. So why did I get this parameterization when I was doing my little application demo, right? So I got 10,000 executions plans there for 10,000 queries, and here I had 2 queries, but yet I got 1 execution plan. Well, those plans here were simple and safe for what is called a simple parameterization. So simple parameterization has a lot of limitations. The first and biggest one is that it works for single table queries only. The moment you have 2 tables involved, the simple parameterization does not work for you. So, let me just quickly go back to my slides. What's inside the procedure cache? It's actually 4 different procedure cache stores. There's no single procedure cache, but there are 4. The most important ones are the first 2, cache store object CP, object plans, and cache store SQL CP, which are SQL plans. So basically, object plans, anything that's an object in the database. Plans for your procs, for your triggers, for your functions. Everything that is not an object, that's a SQL cached plan. Independently, whether it's ad hoc or prepared. The procedure cache steals buffers from the buffer pool, right? So it grabs the buffers from the buffer pool, so they will not be used for caching your data. We have some very young people in the room. Hello, you like SQL Server? Awesome. I wish I could start that age. No. Microsoft Certified Master by the age of 16. Okay. The entries in this cache, in those caches, are aged out based on the cost of compilation, not execution. 2 different costs. The cache entry for your plan has a cost attached to it that describes how difficult it was for the optimizer to come up with this thing. And it's based on the number of context switches that were performed during optimization, number of reads that were done for the metadata, etc., etc. And there is a complicated formula that is described on the programmability team blog. And they do some little mambo-jumbo, and they come up with a number. And that number describes basically what is the cost of replacing this. If I throw this plan out and then I have to recompile it, how difficult it will be. So we're trying to keep the expensive, complicated plans around longer than the ones that are trivial and very easy to come up with. You can actually see this in sysdm memory cache entries, OS memory cache entries. So as I mentioned before, of course, there is another separate cache for the actual text of your queries. It's called SQL Manager, and it's one-to-many with your execution plans. Yes, another question here.
Sorry, but time isn't a factor at all? Doesn't play into the formula at all?
Time it does, because the longer you compile, the more context switches. So it's not based on time per se.
No, I'm sorry, I mean age. So I mean, if we had to use the plan for, a month,
If you didn't have memory pressure, that would decrement this counter, right? And then you will not push it out. So that's part of the problem with the execution, with the plan cache, is that you may have a lot of execution plans there that are single use, so they are basically worthless. But if there is no memory pressure within the procedure cache, they will not be forced out. So they will stay around. What happens is that every time, I actually have it, it's described here. Basically, every time you use the plan, the counter is incremented. For procedural plans, it's always basically put back to whatever was the cost. Every time you need to find place for a new plan in cache, there's a clock hand that moves. As it moves, it touches an entry. Every entry it touches, it will divide that counter by 2. The moment it gets to 0, it goes out. The algorithm is kind of self-tuning, right? So the more memory pressure you have, the more often the clock hand moves, and the more aggressively plans are aged out. But the more expensive the plan is to come up with, and more frequently it is used, the more the cost will keep up. So it's basically that usefulness versus the need for memory and the memory pressure that play against each other, right? And there's a little difference between how, basically we try to keep the procedural plans around more than the ad hoc plans. The ad hoc plans will be forced out first because of how they are being costed. There's interesting thing about the size. So depending on the version, the size of the cap, the hard cap of how big your procedure cache might be, is pretty high. It's up to 75% of your total server memory, at least for your first 4 gigs. So that means that your procedure cache or plan cache can get really, really large. And of course, that will have impact on how much data you might be caching and other caches. There's also a limit on the number of items per cache store. So it's as you can see, it's 4 times as many items on a 64-bit server as on a 32-bit server. The interesting thing to note here is that if you don't control what happens with your plan caching and how many plans you have, how many plans your workload generates, you may get yourself in a situation where most of your memory is being consumed by that execution plan cache. And those cache plans may actually not necessarily be useful. There is no direct control over that. Right? There is no configuration knob. There is no SP configure, set max, plan size, something like that. We've been asking for it. I mean, myself and my fellow MVPs, we asked, like, just give us a knob, SP configure, yada, yada, yada. They said, no, not going to happen. Because there are other means. You're supposed to, get around this problem by other means. Actually, there used to be a percentage knob in 6.5. In 6.5, there was a configuration option that would allow you to set that. In 2000, in newer versions, you don't have that, right? You have this hard cap that is percentage, and then you have to rely on those automatic algorithms that will decide what's useful and what it's not. And they don't always work, right? Depending on your workload, they might not be solving your problem. So it's difficult. Actually, it's like, why don't you give us that knob? And they go like, because we don't want to turn SQL Server into Oracle. Because the moment they give us this knob, we're going to ask for 5 more, right? Then we'll want to have a configuration option for another thing and another thing. And before you know it, we're going to have Oracle. And a lot of configurations options that no one really knows how they work together and play together. Question?
If I use with re-compile in a stored procedure that's doing a dynamic parameterized query, can I expect that to not be cached?
If you use with recompile on anything, it's never cached. So it's a one-off plan. Compile, use, throw away. It never gets into cache. Another question here. It's a CLR stuff is a completely different topic. So there is a cache for CLR, right? But it's nothing to do with those execution plans that we are describing here today, really. Yes? Yes, I'll show you that in a second. Now, I should be finishing in like 7 minutes. I'm maybe 2/3 through. So you guys want to stay with me, and you're fine with me going on, right? Okay. So the official version from Microsoft is that if you have basically this plan cache inflation issues, right, it gets too large because you have a lot of ad hoc stuff, what you should be doing, you should be using resource governor. Resource governor sets memory limits. Those limits are on execution memory and procedure cache. You'll actually see in procedure cache there is a pool ID. That means which part, your cache will be divided by pools, and then you can limit the size of individual pools. Now the problem, of course, with that is Enterprise Edition only. So what about the standard guys? Okay. So how is the procedure cache cleared? It's cleared due to certain database operations. And let me show you that. There's actually an official knowledge base article that describes this. And it's the knowledge base article says, you may experience a decrease in query performance after you perform certain database maintenance operations or regular transaction operations in SQL Server 2005. So they basically tell you, well, if your cache gets cleared, and it will if you do certain stuff, your performance will suck. Why? Well, because now you're recompiling everything that comes in, right? So if you do DBCC free proc cache, or you do one of those things and your cache gets flushed, you can literally see in Performance Monitor how your CPU spikes up and your throughput goes down, right? Because all of a sudden you're recompiling everything. But the best is the list, and I'll not show you the list from the knowledge base article, but from the programmability team blog. And listen to this. The following database operations will flash the plan cache. Alter database, set online, offline, read only, read write, modify file group, collate, drop database, restore database, detach database, anything, right? Restoring any database on a server will flush your entire proc cache for the entire instance, SQL Server 2005. 2008, it's fixed, right? It's better. But the best one is at the end. In SQL Server 2005 RTM and SP1, executing DBCC checkDB will flush your cache. That has to be Pulse-Randolph, right? So, as I mentioned, this is fixed in 2008 for most cases because it doesn't flush the entire cache but individual databases. And how do you know? Well, it's so bad that they actually put that information in the error log. And there's this log that says, SQL Server has encountered so many occurrences of cache store flush for this due to some database maintenance or reconfigure operations. So this is really nasty. You don't want to do that. Of course, you can also do it manually, but why would you? Well, if you have a problem with too many execution plans, then you might want, it's a kind of a last resort. I'll show you a better way, but it's a last resort kind of thing. My plan cache gets too large, so I'm going to clear it every now and then. I know I'm going to take a performance hit, but at least I will be able to reclaim all this memory. Because if you remember, my execution plan, I probably don't have it anymore, but let me see. If I execute my little application again, in 30 seconds, it will give me those 10,000 plans and 900 megabytes. Single application, 30 seconds, 900 megabytes consumed on the server. Just like that. Ouch. Right? So what do you do? Well, you can do DBCC free proc cache, but then you're going to take a hit. So what you can do better is you can do DBCC flash proc in DB. Undocumented, unsupported, so you haven't heard it from me. Don't come back. Complaining, right? Individual database. Right? We're going to just clear AdventureWorks and leave everything intact. Another way that I came up with is this one is actually documented. I mean, the DBCC free system cache is documented, but not this usage. DBCC free system cache allows you to clear individual cache. Because the pros cache, the execution plan, I show you, right? There are 4 different cache stores. You can clear one of them. As in, you can clear the plans for ad hoc stuff and leave the stored procs intact. Because they live in 2 different cache stores, you can clear that individual cache store without. I'll take the questions at the end because I really want to get through, right? We'll probably stay here until like 7:30, so don't worry. So, generally speaking, plan reuse is a good thing, right? We want it, less time spent, but sometimes it might also get nasty. I'll show you that. So, depending on your application, achieving proper plan reuse might be easy or difficult. You actually should be building your application and you should be coding your queries with the plan reuse in mind and deciding when to reuse plans and when not to, because there are also drawbacks. So, what is the drawback? When it's not a good thing? Well, if you cache a plan, that plan has been compiled for some value, typically. It was compiled for a particular parameter value that was submitted upon first execution. It's known as parameter sniffing. Parameter sniffing is basically the optimizer, knowing that there is a parameter, sniffs the value and assumes that this will be the value that you will be executing for and optimizes for that value. So what is the value of your parameter during first execution will determine how your execution plan will behave. And that will get cached. And then it gets executed for a different parameter value. And guess what? It doesn't work anymore, right? Because you had 5 rows here, and then you have 100,000 rows over there, depending on the parameter value, and it gets nasty. So you have to be careful. How do you know? Estimated number of rows, a lot smaller than the actual number of rows. That's one thing, but we already know that this happens also when we don't have a good estimation. So another situation, another way to spot it is that you have a fluctuation, big fluctuations in the number of rows returned, or number of reads in general. In SQL Server 2012, they actually have a new column in dmexec, the query stats. dmexec query stats, they have a new column that gives you the last, minimum, and maximum number of rows returned. So you can know if you have a query that, depending on the parameter value, returns 5 or 5 million rows. You know how bad it can get? I've actually tested it with my client, and I created a pathological situation on purpose just to see what will happen. Executed with 2 edge cases. Executed first with a parameter that had a very small number of rows, and then executed exactly the same plan, knowing that it will be cached for another parameter that had a lot of rows, just to see what will happen. I gave up after 3 days. Killed the query after 3 days. It was trashing the server. So the first execution was like 5 seconds. And then the other one was running for 3 days before I gave up. And before I killed it, I went to sysdmexec requests. And there is a number of reads performed in that DMV. So it shows you how many reads were performed by the query that is running. That number overflowed and went negative. All right. So what do you do if you have a bad plan issue? Bad plan issue meaning you have a parameter sniffing that determines how your query is going to get executed. And that is not a good way for all your cases. First of all, you can always recompile. Not a good thing. Probably you don't want to do that. But sometimes you have to. Right? If you have a query that has these extreme cases, it will go from one end of the spectrum to another, where the way of executing depends on what the parameter is, and you must be sure that you always have the right plan. Yes, you want to recompile every time, taking into account what is the value of your parameter. Masking parameters through local variables. It's actually a way around parameter sniffing that has been around for a while, right? Rather than use a parameter value in the stored proc in your query, you take that parameter value, you put it in a local variable, and then you use the local variable in your query. What it means? When the compiler compiles your stored proc, it knows the value of the parameter, but not the value of the variable, because that hasn't been assigned yet. Right? Your variable is assigned at runtime, so during optimization we don't know the value. So you've just masked the parameter value from the optimizer, basically blinded it, and not knowing that value, the optimizer will have to assume whatever is your median average distribution, right? It will not optimize for a particular parameter, but it will say, like, what is the distribution of this column, right? What is the average number of rows that any value can return? And then you will have a more or less universal plan. That still may not work for your edge cases. Also, you can specify a value for the optimizer to a hint. There's an optimize for hint where you say, I want this thing to be optimized for this value, or in case of SQL Server 2008, optimized for unknown, which is exactly the same of what I just described with the variable. We don't know, or we assume that we don't know the parameter value, so we just go on. How do you control plan caching? Application-side parameterization, explicit. So basically, if I take my little application, and notice this, now I have 10,000 execution plans, 900,000 bytes. But if I was a good developer, I would actually explicitly parameterize my application, my query in the application. I execute this, and I get performance that is equal or very similar to that of a stored proc. And I get one universal execution plan. Let me show you that execution plan. There's one universal execution plan with 10,000 executions. Right here, it says prepared because it's been parameterized, and this is a parameterized version of my query. This is explicit parameterization in the application, right? Using ADO.NET, parameters collection, all that stuff, right? This is the same thing that you would do through SP-execute. If you use SP-execute and you explicitly define your parameters, that's exactly the same thing. ADO.NET internally uses SP-execute SQL to execute your parameterized queries. Another thing you can do, stored procs. Good thing, right? Stored procs get their execution plans cached. There are actually certain advantages of using stored procs over even parameterized ad hoc stuff. Temp table caching can be one of them. Actually, you know what is the biggest reason to use stored procs? I mean, of course, if you want to convince your developers to use stored procs, I can give you my little application. You can run it against AdventureWorks. You'll have this wow factor when they see the performance difference, right? There's a reason in performance, but I believe that the biggest reason for use of stored procs is what the object-oriented programmer would call encapsulation. It's a layer of abstraction over your stuff in the database. As long as you keep that contract, right, the interface of your stored proc does not change, you can do anything you want with it. You can normalize or denormalize or refactor your database, right? You can split your tables, etc., etc. You rewrite the query in the stored proc, the application is fine. So you can do changes in the schema of your database without having to recompile your application. And this is what the programmers do in their object-oriented design because they never expose the details of the implementation. They expose methods, right? It's called encapsulation. You want to do something? Here's a method to do it, right? Call that method, and how it is internally implemented is none of your business.
But if you return a table, it would believe you with only one row back, and that might be wrong.
What, the stored proc? No. The store. No. You're confusing things with the table function, table valued function. Store at proc, right? You execute a store at proc. Store at proc is not part of a query. Yes. Okay. Another thing that you can do is called forced parameterization. Forced parameterization is this beautiful thing. Let me show you. If I execute my ad hoc stuff, right, and let me just do 1,000, right? This is normal what I have right now. It takes 3 seconds to execute 1,000 queries because I get 1,000 separate execution plans. But if I turn on my forced parameterization on this database, this is a database level option. I haven't changed anything about my application. By the way, just to prove it, my procedure cache, my execution plan cache was cleared when I set that option. It cleared the cache. So now I'm doing exactly the same thing, but I'm that much faster. Parameterization, depending on what is your workload, what is your application, parameterization forced might be your ultimate turbo switch for SQL Server. It's like on the old computers we had this turbo switch. It behaves like that for SQL Server. I've seen workloads where we've been able to do 4 times as many batches per second, and our CPU usage was 50% of what it was previously. Because all of a sudden you're not doing the whole bunch of optimizations. Questions at the end. Another option is new in 2008. It's called Optimized for Ad Hoc Workloads. Well, that's not going to speed you up, but it will help you with the problem of getting your plan cache inflated by those single-use plans. So if you have execute something once and then you keep it in cache, there's no point. So what this option does is that at first execution, only an plan stub is cached, basically an information that, yes, we have executed a query like that. Then only at the second execution of the same query, we go like, this is second time, so this is something repeatable. This is a query that is not a one-off. So that thing will benefit from plan caching. And only upon second execution, we actually cache the plan. So if I do this, and let me just quickly set my database to simple. And then normally, it would go like this. First execution, 3 seconds. Second execution, quick, because I'm reusing the same plans. So now I have 1,000 plans, each of them used twice. I executed the same queries. But if I say optimize for ad hoc workloads, then my first execution, I have to clear this. I forgot to do reconfigure. There we go. Then my first execution takes 3 seconds, and at the end of that first execution, I have a bunch of plans that are called compiled plan stub, and they're only 300 bytes each. And there is actually no execution plan for this. I mean, I can see the text of the query, but there is no execution plan because there was nothing cached. The only thing that was cached is the information that, yes, we have executed this. The second time I execute it, it's still slow because I'm still doing 1,000 compilations, but this time I actually put those plans in cache. So this is an option that will affect how your ad hoc queries are being cached. Not on first execution, but only on second execution they get cached. So you can get rid of all those one-time, one-off execution plans. Sorry? Of course I can run it the third time, and the third time it will behave as expected because everything now is cached.
And they still age out, right?
They still age out normally. So those two options, very interesting. You can actually use them in combination. They're independent, but you can have both of them turned on at the same time because they work on different levels and they do different things. Now, you might be wondering, like, okay, so if the forced parameterization is such a super turbo switch for SQL Server, why is it not on by default? And the answer is, again, you might, by reusing execution plans, you expose yourself to that risk that, well, you will have something that, if you compile it for that parameter value is great, but if you compile it for a different parameter value, then it's going to suck. So if they turn it on by default, there is a whole bunch of workloads that would just tank. So you have to do it. You have to test your workload. You have to see if you don't have those queries that with a cached plan, they would get really bad. And then you make a decision whether you turn that option on or not, depending on your workload. Recompilation. Every now and then your plans will get recompiled. Why? There are two reasons. Either the plan is no longer correct, which means you had a schema change or a set options change or something like that, right? If you start executing your plan and then you drop a table or create an index, then you had a schema change that affects the correctness of your plan. Your plan does not reflect what you have in the database. The second reason is optimization. So your plan is no longer optimal because the optimizer knows there's been a change in the distribution of your data. Namely, your statistics have been refreshed. If you refresh your statistics, any plan that during compilation used a particular statistics has to be recompiled to reflect the new information about the data distribution. Knowledge base article 1955-65 describes how the statistics are refreshed and under what conditions. And the 20% rule applies to all the versions since SQL Server 7.0. So how do you know if you have a problem there? Right? All this stuff that I've described, how do you know you have a problem? First of all, you have high CPU usage on your database server. I mean, database servers in general are not CPU bound, right? So if you're trashing CPU on your server, you probably have a problem. If that trashing is because of the high number of compilations per second, well, obviously there is something that you should be doing about your planned reuse. High number of resource semaphore query compile waits. So that means, again, you're doing too many big compilations in a unit of time and you're waiting in a compiler queue. Not a good thing. You don't want to do that. High number of cached plans with use count 1. If you keep a lot of stuff in cache that you're not reusing, you're wasting your memory. You want stuff that you're reusing. Otherwise, there is no point. And high number of cache plans that have the same query hash. Query hash basically describes the type of query. If you don't have a good parameterization, either explicit or forced, then you will have the same plans like I have, 10,000 values, 10,000 execution plans. But it was all the same query. And it would have the same query hash. Because it only differs by the parameter value. If you have a high number of individual plans for the same query hash, you obviously have a problem there because you're not parameterizing your plans correctly. So obviously you might have a problem with execution plan reuse. And you solve this problem through A, explicit parameterization on the side of your application. So work with your developers, explain to them how they should be parameterizing their queries. Even better, stored procs. Forced parameterization as a kind of a, if you cannot affect this application, right? The developers won't talk to you, right? They're autistic, they don't understand. Been there, right? Exactly. So, or this is a vendor application, the source code is not available, or we will take 6 months to go through a change cycle or something like that. Turn on forced parameterization on the database, see what happens. In a lot of cases, you will see a huge improvement. Optimize for ad hoc workloads to get rid of those one-off plans, and then resource governor to set the limits on your resource pools. Query hints. If you hint your query with optimize for, or you can hint your query with parameterization, or through the plan guide, you can hint your query with parameterization forced. You can force parameterization on a certain class of query. Not everything that goes in a database, but you say, here is a template for my query. Here is what the query looks like. Anything that looks like this, I want it to be forcefully parameterized. And you do that using plan guides. Force parameterization is available in SQL Server 2005. That's where it's been introduced. And it really works beautifully. So I hope you liked it. Sorry for overflowing the time. And this is some additional reading, a couple white papers and knowledge-based articles. And by the way, there's one last demo I wanted to show you. Here's how you optimize the optimizer. Remember my 17-second query that was taking so long to optimize? This beautiful execution plan here. So here is what you could do. If I add a hint to every join and say inner loop join, I'm effectively narrowing the space of possible plans. I basically tell the optimizer what to do. It doesn't have to search and come up with the idea. And all of a sudden, instead of 17 seconds, I only have 700 milliseconds of optimization time because I ruled out the whole world of possibilities out there. And I basically told the optimizer what to do. And it's like, okay, here's how we're going. This is how you want us to execute. That's fine. And then all this, basically you narrow the search space for your execution plans. This is, of course, an extreme case. But even if you do it for smaller queries, you can still cut on your execution plan if you add a hint to your query. That hint might be obvious. It might be something that the optimizer is doing anyway. But guess what? It's spending a lot of time to come up to that point where it's doing it. So if you point it in the right direction, it will be faster. Thank you very much for coming. Don't forget to fill out the evaluation forms and give it to the person at the door, or they're probably gone already. And if you want to meet me tomorrow at the Birds of a Feather sessions, you know, those round tables for open discussions, I'll be hosting a SQL OS table, so we can talk everything SQL OS-ish. And I hope to see you guys there, and if not, I'll see you at the party tonight maybe.